Hi there, I'm Dylan, and today I'm going to present to you Lab 3, Circuits. So the purpose of this lab is to examine the behavior of resistors and capacitors, predict the behavior of circuits containing resistors in series and parallel, and use multimeters to measure the value of current and potential differences in circuits, all while using the loop rule and charge conservation. So a preview of the results. So the current in the simple circuit turned out to be 0.02 amps, and the RC value turned out to be about 5.89 seconds. The first simulation followed the loop and node rules, and we also find that the larger resistance causes the capacitor to take longer to charge and discharge, which we will see in the second simulation. So the concepts that we're going to be using are Ohm's law, which entails that the potential difference is directly proportional to the current as well as the resistance. The node rule, which means that the current in equals current out. The loop rule, which means that the potential difference of an entire loop of a circuit is equal to 0, and the capacitance, which means that the potential difference is equal to Q over C, which should be charge over coulombs. So in the first simulation, we're given a circuit with 2 ammeters and 2 resistors. So we have to predict the currents I sub 1 and I sub 2 given the resistances of the 2 capacitors and both of the charges of the batteries being 1.5 volts. So with the calculation, we can find out that I turns out to be 0.0204 amps, and also both ammeters also read 0.02 amps, matching the calculation above. When the connection to an ammeter was inserted backwards, it would read negative 0.02 amps. And so when we add a voltmeter, it would read 3 volts, but the ammeter would read 0 amps. That's because the circuit is open, thus having no flow of electrons, but the voltmeter still maintains that reading of 3 or negative 3 volts because of the potential difference of the batteries and the placement of the probes. And in the next part, we had to find the potential differences between each part of the circuit. And so we find that the circuit maintains the loop rule, which was given by the sum of all the potential differences, and the current is still 0.02 amps. And with the graph, we can see that it slopes down a little at first, and after that it goes down to 0, and that kind of also displays the following of the loop rule. So the ammeter reading does not change when the voltmeter is attached, since the voltmeter does not alter the potential difference or current, and the voltmeter reads negative 2.04 volts when connected across the 100 ohm resistor. And with the parallel ammeter, the ammeters now read 0.06 amps instead of 0.02 amps, since not all electrons flow through the resistor, now that a parallel ammeter has been introduced into the circuit. And when we calculate resistances of each element, we find that the 47 ohm resistor has a resistance value of 48 ohms. The 100 ohm resistor has a resistance value of 102 ohms. The wire and the ammeter have resistance values of 0 ohms. In the next part of this lab, we have an RC circuit. So we're given a 9-volt battery, 10 ohm bulb, 20 ohm bulb, and 0.2 farad capacitor. So when the battery was disconnected from the circuit, the bulb turned on and slowly dimmed. So with the 10 ohm bulb, the time to charge the capacitor was 10 seconds, and the time to discharge was about 9.7 seconds. With the 20 ohm bulb, the time to charge was about 12 seconds, while the time to discharge was about 11 seconds. And in part 2, we're kind of given the calculation of natural log of the potential difference over the potential difference naught versus time graph. We find a slope of negative 0.17, which gives us an RC value of about 5.89 seconds. So what if the experiment was done in real life and a real ammeter was used? So since a real ammeter would have a higher resistance than a simulated one, the current that it would read would be smaller than what would appear on the simulation. And what if the experiment was done in real life and a real battery was used to charge a real capacitor with no resistor, and the battery would not charge a capacitor as quickly as it would in simulation, since the ammeter and the wire would have some resistance that would make the capacitor take longer to charge. So possible errors and assumptions include the timing and the charge and discharge of the capacitor. It was a human task and not done by the computer. And we also assumed that resistance among the ammeter and wires are negligible, and that there's steady state in the circuits without capacitor. And that's it. Thank you for watching, and have a nice day.